Imagine, for a moment, that everything you know, every star you can see in the night sky, every galaxy that our most powerful telescopes can resolve, is but a single grain of sand on an impossibly vast beach. This grain of sand is our universe. It is sprawling and majestic, stretching across more than 90 billion light years, a distance so large it is almost incomprehensible, roughly equivalent to 550,000 million miles, or 880,000 million kilometers. It contains perhaps 2 trillion galaxies, each one a swirling city of stars. Yet, for all its grandeur, it may be just that, a single isolated island in a cosmic ocean of unimaginable scale. We would love to know where you are listening from on our own small island in the cosmos, and what time it is there, so please let us know in the comments. And if you enjoy pondering the grandest questions, be sure to subscribe, and we will let you know when our future stories are released. This vast cosmic ocean is the stage for one of the most profound and controversial ideas in all of science: the multiverse. The concept of the multiverse suggests that our universe is not alone. It proposes that it is just one of a potentially infinite number of other universes, each existing alongside our own, perhaps separated by dimensions we cannot perceive, or by distances we can never hope to cross. In some of these other worlds, the laws of physics might be subtly different, leading to realities starkly alien to our own. In others, they might be identical, giving rise to countless worlds where copies of you and I are living out lives that diverged at some critical, long-forgotten moment. This is not merely the stuff of fiction. It is a hypothesis that arises naturally from our best and most current theories of cosmology and quantum physics, a startling implication of the very mathematics we use to describe our own reality. It forces us to confront the possibility that the Big Bang, the cataclysmic event that gave birth to our cosmos some 13.8 billion years ago, may not have been a unique event at all, but just one of many. This story is not about proving that the multiverse is real. Instead, it is the story of an idea, a journey tracing how humanity came to even conceive of such a possibility. It is a tale that stretches back thousands of years, long before the advent of modern science, and winds its way through some of the greatest intellectual revolutions in human history. We will travel from the bustling markets of ancient Greece to the hallowed halls of Renaissance Italy, from the atomic laboratories of the mid-20th century to the supercomputers of the 21st century that simulate the very dawn of creation. We will meet the thinkers, both celebrated and condemned, who dared to look beyond the confines of a single world and imagine a grander, more complex reality than the one presented to their eyes. It is a narrative about the relentless human drive to understand our place in the cosmos, even if that place is far more humble than we ever imagined. Our journey begins not with complex equations or powerful telescopes, but with the simple yet revolutionary power of philosophical inquiry. To find the very first seeds of the multiverse concept, we must travel back in time more than 2 millennia, to a world lit by oil lamps and powered by human hands and minds. It was here, under the warm Mediterranean sun, that a school of thinkers known as the atomists first dared to propose a cosmos of infinite possibility. They argued that if the fundamental building blocks of reality were just atoms moving through an infinite void, then it stood to reason that they must have arranged themselves into countless other worlds, some similar to ours, some wildly different, scattered throughout the endless expanse. This was the first tentative step on a long road, a philosophical echo of a scientific debate that rages to this day. The main wellspring of this revolutionary thinking can be traced to the city of Miletus, a bustling Greek port on the western coast of Anatolia, in modern-day Turkey. But it was truly championed and expanded upon by a man named Democritus in the 5th century, before the Common Era. He hailed from the colony of Abdera in Thrace, and his thinking was built upon the foundations laid by his shadowy mentor, Leucippus, a figure so enigmatic that some later historians even questioned his existence. Together, they imagined a universe that was profoundly simple in its construction, yet infinite in its expression. Theirs was a reality composed of only 2 fundamental elements: atomos, meaning uncuttable, which were infinitesimally small, solid particles of countless different shapes and sizes, and keinon, the void, an absolute and endless emptiness in which these atoms moved. This was a radical departure from the prevailing thought of their time, which held that a true vacuum was impossible, and that the world was a plenum, entirely full of matter. For the atomists, however, the void was not just a possibility. It was a logical necessity. Without empty space to move through, the eternal dance of the atoms, their constant collisions, entanglements, and separations would be impossible. In their view, every object, every person, every star was simply a temporary arrangement of these fundamental particles, a fleeting congregation in the endless cosmic expanse. This seemingly simple framework of atoms and the void led Democritus to a staggering and unavoidable conclusion. If the number of atoms in existence was infinite, and the void they inhabited was also infinite in extent, then it was a matter of her statistical inevitability that they would combine in every conceivable way. Over an infinite span of time, they would not and could not form just one world, our world. Instead, they must give rise to an infinite number of worlds, or cosmoi, as they called them. He imagined these worlds scattered throughout the infinite void, each one a unique cosmic experiment. Some, he speculated, would be much like our own, teeming with life, complete with a sun and a moon. Others might be barren, lifeless husks of rock. Still others could be vastly different, worlds without water, or worlds where multiple suns and moons hung in the sky, or even worlds where strange and monstrous creatures composed of different atomic arrangements lived and died. He saw these worlds as being in a constant state of flux. Some were in the process of being born, growing as more atoms were drawn into their gravitational embrace, while others were in their prime, and still others were decaying, colliding with other worlds and dissolving back into the primordial chaos of individual atoms. This grand vision was not born from divine revelation or mystical insight, but from the relentless application of logic to a set of simple physical premises. It was one of the first attempts in human history to explain the totality of existence without resorting to supernatural creators or divine purposes. The ideas of the atomists, however, did not flourish in the intellectual climate of ancient Greece. They were soon overshadowed and actively suppressed by two of the most influential thinkers in all of Western history, Plato and his student, Aristotle. In the 4th century, before the Common Era, their philosophies came to dominate Athenian thought, and eventually the entire Western world for nearly 2 millennia. Plato vehemently rejected the atomists' mechanistic and materialistic universe. For him, the reality we perceive was merely a flawed and shadowy reflection of a higher, perfect reality he called the world of forms. He believed in a purposeful creation designed by a divine craftsman, the demiurge, who modeled our universe on a single, perfect, and unique blueprint. In Plato's teleological worldview, the existence of multiple, random, and imperfect worlds was simply nonsensical. It would imply a flawed or indecisive creator. Aristotle, building on Plato's foundations, constructed a comprehensive model of the cosmos that would become dogma for centuries. His was a finite, geocentric universe, with the Earth fixed at its very center. He argued that all heavy matter had a natural tendency to move towards this one, single cosmic center. Consequently, the existence of another world, with its own center, was a logical and physical impossibility. If another Earth existed somewhere else, its matter would naturally try to move towards our Earth, the true center of all things, thus rendering the idea of a stable, separate world absurd. The sheer intellectual authority of Plato and Aristotle was so immense that their single universe model was adopted not just by later Greek and Roman thinkers, but was also integrated into the theology of medieval Christianity and Islam, effectively burying the atomists' pluralistic vision for over 1,500 years. Despite this overwhelming opposition, the idea of infinite worlds was not entirely extinguished. It was kept alive and even refined by a philosopher named Epicurus, who in the late 4th and early 3rd centuries, before the Common Era, founded a school in Athens known simply as the Garden. It was a tranquil retreat just outside the city walls, a place where he and his followers could pursue a philosophy aimed at achieving a life of tranquility and freedom from fear. Epicurus adopted the atomism of Democritus as the physical basis for his ethical system. By teaching that the universe was nothing more than atoms in a void, governed by natural laws, he sought to liberate people from the terror of capricious gods and the dread of divine punishment after death. But he also introduced a crucial new concept to atomism, the Kleineman, or the swerve. He proposed that as atoms fell through the void, they would occasionally and unpredictably swerve just a tiny bit from their otherwise straight paths. This random deviation was just enough to allow for atoms to collide and form complex structures. But more importantly, it introduced an element of genuine chance and indeterminacy into the universe. This broke the chains of rigid determinism implied by Democritus's original theory, and for Epicurus, provided a physical basis for human free will. Following the same logic as his predecessor, Epicurus argued that this infinite, random dance of atoms must inevitably produce an infinite number of worlds. This idea found its most powerful and beautiful expression several centuries later, through the work of the Roman poet and philosopher Titus Lucretius Carus. In the 1st century, before the Common Era, Lucretius penned a magnificent epic poem titled De Rerum Natura, or On the Nature of Things. In its 6 books, he laid out the Epicurean worldview in stunning verse, creating a masterpiece that stands as the most complete surviving account of ancient atomism. Lucretius explicitly and passionately argued for a plurality of worlds, writing that one must confess that there are other worlds in other parts of the universe, with different races of men and different species of wild beasts. For him, our world was not a divine creation, but a natural, and therefore repeatable, accident. The same forces that brought our Earth into being were at play everywhere in the infinite void, and it was sheer arrogance to assume that our home was unique in all of creation. Yet, for all its poetic power, Lucretius's vision would fall silent for more than 1,000 years, a casualty of the Roman Empire's decline and the subsequent rise of a new, monolithic intellectual authority. Through the long centuries that followed, the finite, earth-centered cosmos of Aristotle, now sanctified and woven into the very fabric of Christian theology, held absolute sway. The universe was seen as a divine and orderly creation, a celestial clockwork with humanity placed purposefully at its heart. To suggest otherwise was not simply an error in reasoning. It was a profound heresy, a direct challenge to the established order of both heaven and earth. The scattered, infinite worlds of the atomists were forgotten, dismissed as a pagan absurdity. It would take the cultural and intellectual upheaval of the Renaissance, a fervent period of rediscovering the lost knowledge of antiquity, to pry open the lid of this closed, comfortable cosmos. And the man who would ultimately shatter it, not with telescopes or mathematical proofs, but with the sheer, explosive force of his philosophical imagination, was a Dominican friar from the south of Italy, a man named Giordano Bruno. Born Filippo Bruno in the year 1548 in the town of Nola, a stone's throw from the volcanic shadow of Mount Vesuvius, he was a figure forged in the intellectual ferment of his time. He came of age as the rediscovery of ancient texts, including Lucretius's De Rerum Natura, was inspiring a new generation of thinkers to question long-held assumptions. At the age of 17, he entered the Dominican order in Naples, taking the name Giordano, and was quickly recognized for his prodigious intellect and a truly astonishing memory, which he trained using complex mnemonic techniques. But within this devout and structured environment, his mind was a restless and untamable force. He read voraciously and dangerously, devouring forbidden texts and developing a deep-seated contempt for the rigid dogma that surrounded him. He questioned sacred doctrines, from the nature of the Trinity to the divinity of Christ. And his sharp tongue and defiant spirit soon brought him into conflict with the monastic authorities. Accused of heresy, he was forced to flee in 1576, shedding his friar's habit and embarking on a life as a wandering scholar, a journey that would take him across the great intellectual centers of late 16th century Europe. For the next 15 years, Bruno was an intellectual nomad, a man perpetually in search of a patron who could tolerate his radical ideas. He journeyed to Geneva, but his uncompromising nature quickly drew the ire of the city's strict Calvinist leaders. He found a temporary haven in France, where he gained the favor of King Henry III, who was fascinated by his art of memory. He then traveled to England, where he lectured at Oxford, fiercely debating the dons who still clung to an antiquated Aristotelian worldview. It was during his time in London that he published some of his most important and incendiary works, dialogues in which he began to fully articulate his revolutionary vision of the cosmos. From England, he moved on to Germany, teaching in Wittenberg and Prague, always challenging, always provoking, and always making powerful enemies. He was a man of immense courage and infuriating arrogance, a philosopher who saw himself as a herald of a new dawn, tasked with awakening the world from its long, dogmatic slumber. He was not a scientist in the modern sense. He was a mystic, a philosopher, and a magician in the Renaissance sense of the word, one who believed in a universe animated by a divine spirit, a single, infinite entity that he equated with God. This theological belief was the very foundation of his cosmology. For Bruno, the notion of an infinite God creating a finite universe was a logical contradiction, a limitation on the Creator's own omnipotence. An infinite and eternal divine power, he argued, must necessarily express itself in an infinite and eternal creation. He took the sun-centered model recently proposed by the Polish astronomer Nicholas Copernicus and pushed it to its logical and terrifying conclusion. Copernicus had dislodged the Earth from the center of the universe, but he had kept the cosmos small and contained, enclosed within a final, outermost sphere of fixed stars. Bruno smashed this crystalline sphere to pieces. He declared that the universe was infinite in all directions, with no center and no circumference. Our sun, he insisted, was nothing special. It was merely one star among countless others, a nearby sun that appeared brighter only because of its proximity. Each of the twinkling points of light in the night sky was another sun, equally vast and brilliant, scattered through the endless depths of space. And if they were sunned, they too must have planets circling them, their own Earths and Jupiters, hidden from our view by the immense distances. These worlds, he speculated, were not barren rocks. They were inhabited, teeming with their own forms of life, their own plants, animals, and rational beings. This was a universe not just of infinite space, but of infinite life, a concept that completely decentered humanity and directly contradicted the unique salvific story of Christianity. If there were infinite worlds with intelligent beings, had Christ also been incarnated on each one? The question was so profoundly heretical that it shook the very foundations of the Church's authority. After years of wandering, a fateful invitation drew him back to his homeland, a decision that would seal his doom. He was asked to come to Venice to teach his famous art of memory to a nobleman named Giovanni Mocenigo. But Mocenigo, a man of unstable temperament, became frustrated when he felt Bruno was withholding his secrets. Embittered and perhaps frightened by his tutor's blasphemous ideas, he betrayed him, denouncing Bruno to the Venetian Inquisition in 1592. The trial that followed was a grueling and protracted affair. After being held and interrogated in Venice, Bruno was extradited to Rome in 1593, where he was imprisoned in the dungeons of the Holy Office. For 7 long years, he languished in confinement, while the Church's finest theologians, led by the formidable Cardinal Robert Bellarmine, meticulously examined his life's work. They compiled a long list of heretical charges against him, which spanned the full breadth of his philosophical and theological thought. They condemned his belief in an infinite universe and a plurality of worlds, his denial of core Catholic doctrines, and his perceived leanings toward a kind of pantheistic nature worship. Throughout the ordeal, Bruno remained defiant. He was willing to debate and to concede on minor points of theology, but he refused to renounce the core of his philosophical vision, the infinite cosmos that he saw as the only creation worthy of an infinite God. The inquisitors demanded a full and complete recantation, a total submission to the authority of the Church, But it was a price Bruno was unwilling to pay. In the early weeks of the year 1600, the final verdict was delivered. He was declared an impenitent and pertinacious heretic. As his sentence was read aloud, Bruno stared down his judges and uttered the immortal words that would echo through the centuries. "Perhaps you pronounce this sentence against me with greater fear than I receive it." On the 17th of February, in the year 1600, he was taken to the Campo dei Fiori, a bustling public square in the heart of Rome. To silence his powerful voice, his tongue was pierced by an iron spike, and he was bound to a stake and burned alive. His ashes were unceremoniously thrown into the Tiber River, an attempt to erase his existence from the world. But his ideas and the story of his martyrdom could not be so easily extinguished. He had not proven the existence of other worlds, but he had died for the freedom to imagine them, transforming the multiverse from a forgotten philosophical footnote into a powerful and dangerous idea that would haunt the imagination of the coming scientific age. The coming scientific age, however, would be built on a foundation fundamentally different from the one upon which Bruno had stood. It was an age of empiricism, of observation and experiment, a new intellectual world shaped by figures like Galileo Galilei and Isaac Newton. They taught that the book of nature was written in the language of mathematics and could only be read through the lens of a telescope or the careful measurement of falling objects. In this new, rigorous world, a concept like a plurality of worlds, which could not be seen or tested, was relegated to the realm of pure speculation. For more than 300 years, the multiverse idea fell silent once more, a philosophical ghost haunting the hallways of a new science that had no room for it. Physics progressed with astonishing speed, mapping the orbits of planets, codifying the laws of thermodynamics, and harnessing the power of electromagnetism. The universe, while vastly larger than Aristotle's, still seemed to be a single, orderly, and ultimately knowable system. It was not until the dawn of the 20th century that this tidy, mechanical picture of reality was shattered, and shattered so completely that it created an opening for an idea even more radical than Bruno's to re-emerge. This time not from theology, but from the very heart of physics itself. The revolution began in the year 1900, when the German physicist Max Planck, studying the nature of heat and light, reluctantly proposed that energy was not a continuous, smoothly flowing wave, but came in discrete, tiny packets, which he called quanta. This seemingly small technical adjustment to a stubborn mathematical problem would prove to be the loose thread that, when pulled, unraveled the entire tapestry of classical physics. Over the next 3 decades, a new generation of brilliant and often bewildered physicists, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others, descended into the bizarre Alice in Wonderland world of the atom. They discovered a realm where the familiar rules of cause and effect no longer seemed to apply. A ghostly subatomic landscape governed not by certainty, but by probability. They found that a particle like an electron was not a tiny, solid ball orbiting a nucleus. Instead, its properties were described by something called a wave function, a mathematical abstraction that represented a haze of potentiality. According to this new quantum mechanics, until you measured it, an electron did not have a definite position or a definite velocity. It existed in a state of superposition, occupying all possible positions and having all possible velocities simultaneously. The act of observation, the very attempt to measure the particle, seemed to force its hand, causing this cloud of possibilities to instantly collapse into a single, concrete reality. This was the infamous measurement problem, a profound mystery that struck at the core of what it meant for something to be real. To make sense of this baffling behavior, the Danish physicist Niels Bohr, the great patriarch of the quantum revolution, and his colleagues in Copenhagen formulated what came to be known as the Copenhagen interpretation. It became the standard, orthodox view of quantum mechanics for much of the 20th century. In essence, it stated that one should not ask what a particle is doing when it is not being observed. The question was deemed meaningless. The fuzzy, probabilistic world of the quantum wave function and the solid, definite world of our everyday experience were seen as two separate domains, governed by different rules. A quantum system would evolve smoothly according to the elegant mathematics of the Schrödinger equation. But the moment a classical measuring device, or a conscious observer, interacted with it, this smooth evolution was violently interrupted, and the wave function would randomly collapse. This interpretation worked beautifully as a practical tool. It allowed physicists to make astonishingly accurate predictions and build the technologies, from lasers to semiconductors, that would define the modern world. But as a fundamental description of reality, it was deeply unsatisfying to many, including Albert Einstein, who famously quipped that God does not play dice with the universe. It introduced a strange and arbitrary split in reality, a shifty split, as one physicist called it, between the quantum and the classical, without ever explaining where that line was drawn or why the act of measurement held such a special, almost magical power over the cosmos. It seemed as though reality was holding its breath, waiting for someone to look at it before it would commit to existing in a particular way. It was into this deeply perplexing state of affairs that a young, brilliant, and fiercely independent-minded graduate student at Princeton University named Hugh Everett III entered the scene in the mid-1950s. Everett was a student of the renowned physicist John Archibald Wheeler, and he possessed a mind that was not content with the pragmatic, shut up, and calculate ethos of the Copenhagen interpretation. He was profoundly bothered by the wave function collapse. It struck him as an ugly and ad hoc addition to an otherwise beautiful and perfectly logical theory. He saw no reason why the smooth, deterministic evolution of the Schrödinger equation should suddenly be suspended just because a measurement was made. So, he asked a simple, yet world-altering question. What if it is not? What if the wave function never collapses? What if the Schrödinger equation applies to everything, at all times, without exception, from the smallest electron to the largest observer and the entire universe itself? The logical consequences of this single, audacious assumption were staggering. If the wave function never collapses, then every single possible outcome of a quantum measurement must, in some sense, be realized. If an electron in a state of superposition can be found at position A or position B, then when you measure it, the universe itself splits into two distinct copies. In one universe, you find the electron at position A. In the other, a perfect copy of you, in a perfect copy of the laboratory, finds the electron at position B. This was the birth of what would later be called the many worlds interpretation. In Everett's vision, every quantum event that has more than one possible outcome acts as a fork in the cosmic road, causing reality to branch into a multitude of parallel universes. The universe of the observer becomes entangled with the observed particle, and the whole system splits, creating separate, non-communicating realities for each possibility. From this perspective, the world only appears to be random. From a God's eye view of the entire multiverse, there is no randomness at all. Everything that can happen does happen in some branch of reality. This elegantly solved the measurement problem by simply erasing it. There was no shifty split between the quantum and classical worlds, no mysterious collapse. There was only the universal wave function, evolving smoothly and creating an ever-expanding, ever-branching tree of parallel realities. Everett had taken the mathematics of quantum theory to its logical conclusion, and that conclusion was a multiverse of breathtaking scope. He first called his idea the theory of the universal wave function, a title that reflected its grand ambition. However, he was met not with acclaim, but with skepticism and outright dismissal. The physics establishment, steeped in the Copenhagen view, found his idea to be grotesquely extravagant, a monstrous violation of the principle of Occam's razor, which favors the simplest explanation. The idea of creating countless copies of the entire universe every fraction of a second seemed like a delusional fantasy. Even his advisor, Wheeler, who was initially intrigued by the sheer boldness of the concept, grew cautious and convinced Everett to tone down his thesis and rename it the more sober relative state formulation of quantum mechanics, which carefully avoided any explicit mention of splitting or many worlds. In 1959, Everett was given a chance to travel to Copenhagen to present his ideas directly to Niels Bohr himself. The meeting was a complete disaster. Bohr, the aged and revered father of quantum theory, was utterly unimpressed by the arguments of the young American physicist, and refused to even consider the possibility that his interpretation might be flawed. The established community had closed ranks, and Everett's revolutionary vision was rejected. Deeply disillusioned by the experience, Everett left theoretical physics behind for good upon completing his doctorate. He accepted a lucrative position at the Pentagon's Weapons Systems Evaluation Group, where he applied his formidable mathematical talents to Cold War game theory and nuclear strategy. He became a pioneer in the field of operations research, made a fortune, and lived a life far removed from the arcane debates of quantum philosophy. He rarely spoke of his groundbreaking thesis again, and for more than a decade, his work was almost completely forgotten, a strange and obscure footnote in the history of physics. But the seed he had planted, the idea that the strangeness of the quantum world could be explained by the existence of other parallel worlds, would not lie dormant forever. It was a concept too powerful and too elegant to simply disappear. It would be kept alive by a small handful of physicists who saw its potential, and it would eventually be rediscovered by a new generation, finding an unexpected and powerful resonance with emerging theories about the origin of the universe itself, once again transforming our vision of the cosmos. While Hugh Everett's radical ideas were languishing in obscurity, a different kind of revolution was solidifying its hold on the world of physics, one that looked not inward to the strange rules of the atom, but outward to the grandest scales of time and space. By the 1960s, the Big Bang theory had become the consensus model for the origin of the universe. Its triumph was sealed by two critical pieces of evidence: Edwin Hubble's observation in the 1920s that distant galaxies are all rushing away from us, proving the universe is expanding, and the serendipitous discovery in 1965 by Arno Penzias and Robert Wilson of the cosmic microwave background. This faint, pervasive glow of radiation, a cold hiss of static that filled the sky in every direction, was the leftover heat from the primordial fireball, an ancient echo of creation itself. For the first time, humanity had a scientifically robust story of our cosmic origins, a timeline stretching back some 13.8 billion years to a moment of unimaginable density and heat. Yet, as powerful and successful as this standard Big Bang model was, by the late 1970s, a handful of deeply puzzling questions had emerged, cracks in the otherwise elegant edifice of modern cosmology that hinted at a deeper, stranger story. The first of these puzzles was known as the horizon problem. When astronomers mapped the cosmic microwave background radiation with incredible precision, they found it to be astonishingly uniform in temperature across the entire observable universe. No matter which direction they looked, the temperature was the same to 1 part in 100,000, hovering at a frigid 2.725 degrees Kelvin, or about minus 270 degrees Celsius, which is negative 455 degrees Fahrenheit. On the surface, this uniformity might not seem strange, but according to the standard Big Bang model, it was a profound mystery. In a universe expanding at a known rate, regions of the sky separated by more than a couple of degrees are so far apart that there has not been enough time since the dawn of creation for light, or any other kind of signal, to have traveled between them. They were, and always had been, outside of each other's causal horizon. It was as if you walked into a vast, sealed room and found that the air temperature in one corner was identical to the temperature in the opposite corner. 100 meters, or about 330 feet away, down to a fraction of a degree, without there being any connecting vents or circulation system. It implied these disconnected regions had somehow coordinated their temperatures without ever being in contact. A coincidence of astronomical proportions. The second enigma was the flatness problem, which concerned the overall geometry of space-time. According to Einstein's theory of general relativity, the density of matter and energy in the universe determines its shape. If the density was above a certain critical value, the universe would be closed, like the surface of a sphere, and gravity would eventually halt its expansion and cause it to collapse back on itself in a big crunch. If the density was below this value, the universe would be open, shaped like a saddle, and would expand forever, its galaxies growing ever more isolated. Only if the density was exactly at the critical value would the universe be flat, like an infinite plane, expanding forever, but with the rate of expansion constantly slowing, approaching zero. The astonishing fact was that our universe appeared to be incredibly, unnervingly flat. For this to be true today, the density of the universe 1 second after the Big Bang had to be fine-tuned to the critical value to an accuracy of 1 part in 1,000 million million. Any deviation, even an infinitesimal one, would have been magnified over billions of years of expansion, leading to a universe that would have either collapsed long ago or flown apart so rapidly that no stars or galaxies could have ever formed. It was like finding a pencil balanced perfectly on its tip after 14 billion years. Its initial state had to be set with an almost unbelievable degree of precision. It was in an attempt to solve an entirely different problem, that of magnetic monopolies, that a young postdoctoral physicist at Stanford University named Alan Guth had a sudden, world-changing insight in the winter of 1979. He was contemplating the consequences of grand unified theories, which proposed that in the extreme heat of the very early universe, the fundamental forces of nature, except for gravity, were merged into a single superforce. These theories also predicted that as the universe cooled, exotic, super-heavy particles with a single magnetic pole should have been created in vast numbers, yet not a single one has ever been detected. Guth realized that a period of super-rapid, exponential expansion in the universe's first moments could solve not only the monopole problem, but the horizon and flatness problems as well. He called this idea inflation. He theorized that in the first fleeting fraction of a second, when the cosmos was just 10 to the minus 36 seconds old, a tiny patch of space, perhaps a billion times smaller than a single proton, was dominated by the energy of a peculiar quantum field, trapping it in a high-energy state known as a false vacuum. This state of false vacuum had a remarkable property. It exerted a powerful, repulsive gravitational force, causing space itself to expand at a mind-boggling exponential rate. In a mere 10 to the minus 32 seconds, this tiny subatomic patch of space would have doubled in size at least 100 times over, swelling from an infinitesimal point to something at least 10 centimeters, or about 4 inches, across, and it would have continued to expand from there. This explosive burst of hyper-expansion, faster than the speed of light, elegantly wiped the cosmological slate clean. It solved the horizon problem because our entire observable universe originated from a single, minuscule, causally connected region before inflation began. This tiny patch was in thermal equilibrium, and inflation then stretched it to a colossal size, preserving that initial temperature uniformity across vast, now disconnected, cosmic horizons. It solved the flatness problem in the same way an ant on the surface of a rapidly inflating balloon would perceive its world as becoming flatter and flatter. The exponential expansion would stretch any initial curvature of the universe to near perfect flatness, regardless of its starting conditions. And it solved the monopole problem by taking the few monopoles that might have formed before inflation and spreading them out so thinly across this now immense volume of space that the chance of finding one in our observable patch is practically zero. After this brief but violent inflationary epoch, the energy field decayed, releasing its stored energy in a massive flood of heat and particles, which is the event we now recognize as the hot, dense beginning of the standard Big Bang. Inflation was not an alternative to the Big Bang. It was a prequel, a theory that set the stage and established the precise initial conditions the Big Bang model had, until then, been forced to simply assume. Guth's original model, however, had a flaw. He could not find a way to end inflation gracefully. It was a Russian physicist named Andrei Linda who, in the early 1980s, refined the idea and, in doing so, transformed it from a theory about the beginning of our universe into a theory about the endless creation of countless universes. In Linda's model of chaotic or eternal inflation, the quantum field driving this expansion, which he called the inflaton field, does not decay all at once. Instead, due to random quantum fluctuations, it decays in some regions, but not in others. Imagine the inflating cosmos as a vast ocean of this inflaton field. In some patches of this ocean, the field's energy drops, the false vacuum collapses, and a bubble of normal space-time nucleates and begins to expand in a hot Big Bang, forming a self-contained universe. Our universe is but one of these bubbles. But outside these bubbles, in the vast ocean between them, the inflaton field continues to drive space to expand at an exponential rate. As it expands, it creates more room for more quantum fluctuations, which in turn cause new bubble universes to form, each one an island of calm in the eternally raging inflationary sea. The process, once started, never ends. Inflation stops in localized pockets, but globally, it is eternal. This theory naturally gives rise to a multiverse of a truly staggering scale. Each bubble universe could be infinite in its own right, and there would be an infinite number of these bubbles, constantly budding off from the eternally inflating background. Furthermore, the laws of physics themselves could be different in each bubble, as the way the inflaton field decays could vary from one bubble to the next, potentially producing different fundamental particles and forces. The multiverse had returned to cosmology not through philosophy or the splitting of quantum waves, but as a direct and seemingly unavoidable consequence of our best theory for the origin of the cosmos itself. This new conception of the cosmos, born from the physics of the very large, was not the only path that led to the multiverse in the late 20th century. A parallel journey was being undertaken in a completely different realm of science, the quest to understand the very small. For decades, the two great pillars of modern physics had stood in magnificent but splendid isolation from one another. On one side was Einstein's general theory of relativity, a masterpiece of classical physics that described gravity as the elegant curvature of a smooth, continuous fabric of space-time. It governed the majestic waltz of planets, stars, and galaxies. On the other side was quantum mechanics, the strange and staggeringly successful theory of the subatomic world. It described a reality that was fundamentally fuzzy, probabilistic, and granular, a world of jittery particles and quantum leaps. Both theories worked perfectly within their own domains, but they were written in different mathematical languages and were based on incompatible views of reality. This schism presented the single greatest challenge in theoretical physics: the search for a unified theory, a single framework of quantum gravity that could describe all the forces of nature, from the fall of an apple to the inside of a black hole, and the very first moment of the Big Bang itself. The first glimmers of such a theory appeared in a surprisingly roundabout way. In the late 1960s, a young Italian physicist named Gabriele Veneziano was searching for a set of equations that could describe the behavior of the strong nuclear force, the incredibly powerful interaction that binds protons and neutrons together inside an atomic nucleus. He stumbled upon a beautiful 200-year-old mathematical formula, the Euler beta function, which, to his astonishment, seemed to perfectly model the data from particle collisions. No one knew why it worked, but it did. Soon, other physicists, including Leonard Susskind and Yoichiro Nambu, realized that this strange mathematical model was describing something physical. The equations were not describing the interactions of point-like particles, but of tiny, one-dimensional, vibrating objects, which they called strings. This was the birth of string theory, though at the time it was seen merely as a promising, if quirky, model of the strong force. However, this early version of the theory had some serious problems. Its equations stubbornly predicted the existence of a massless particle with properties that perfectly matched those of the hypothetical graviton, the quantum particle of gravity, which had nothing to do with the strong force. Furthermore, the mathematics only worked if the universe contained an absurd 26 dimensions of space-time. These issues were seen as fatal flaws, and by the mid-1970s, string theory was largely abandoned as a dead end, eclipsed by the rise of the standard model of particle physics, which provided a much more successful description of the subatomic world using conventional point particles like quarks and gluons. For nearly a decade, string theory was kept alive by only a small, dedicated group of theoretical outcasts. Then, in the year 1984, a stunning breakthrough by physicists Michael Green and John Schwartz triggered what became known as the first superstring revolution. They revisited the theory and realized that the very features that had been considered its greatest failures were in fact its greatest strengths. That unwanted, massless particle was not a flaw, it was a prediction. They proposed that string theory was not a theory of the strong force at all, but a much more ambitious theory of everything. The particle it predicted was the graviton, making string theory the first mathematically consistent and promising candidate for a theory of quantum gravity. They also showed that certain inconsistencies in the theory vanished if one included strings that described not just force-carrying particles or bosons, but also matter particles or fermions, creating a supersymmetric theory that required 10 dimensions instead of 26. Suddenly, string theory was catapulted from the fringes to the very center of theoretical physics. The idea was beautifully simple at its core. If you could zoom in on any fundamental particle, an electron or a quark, you would not see a point, but a minuscule, vibrating loop of energy, a string. Just as a violin string can vibrate at different frequencies to produce different musical notes, these fundamental strings could vibrate in different patterns, and each vibrational mode would manifest as a different kind of particle. The electron, the photon, the graviton, all the inhabitants of the particle zoo were nothing more than different notes played on a single, fundamental string. This elegant picture, however, came with the unavoidable baggage of extra dimensions. For the theory to be mathematically consistent, the universe had to have 9 dimensions of space and 1 of time. The question then was, where were these other 6 spatial dimensions? The answer was that they were hidden, curled up, or compactified into a tiny, complex geometric shape at every single point in our familiar three-dimensional space. To visualize this, one can imagine a long, thin garden hose. From a great distance, it appears to be a one-dimensional line. But for a tiny ant walking on its surface, it clearly has a second dimension, a small circle that you can walk around. In a similar way, string theorists proposed, our universe has 6 extra spatial dimensions curled up into a shape so small, on the order of the Planck length, which is a millionth of a billionth of a billionth of a billionth of a centimeter, or about a 10 millionth of a billionth of a billionth of a billionth of an inch, that they are completely undetectable to our senses and even our most powerful particle accelerators. The specific geometry of these curled-up dimensions, known as a Calabi-Yau manifold, is incredibly important, as it determines how the strings can vibrate, and therefore dictates the kinds of particles and the very laws of physics that we observe in our universe. By the early 1990s, a new problem had emerged. Physicists had discovered that there were not one, but 5 different, consistent versions of superstring theory, each requiring 10 dimensions. It seemed that the quest for a single theory of everything had led to 5. The breakthrough came in 1995 at a string theory conference at the University of Southern California, during a now legendary lecture by Edward Witten of the Institute for Advanced Study. Witten, regarded by many as the world's greatest living theoretical physicist, proposed a stunning synthesis. He argued that the 5 competing string theories were not different theories at all, but merely different approximations of a single, deeper, and more mysterious theory that existed in 11 dimensions. He called this underlying framework M theory, leaving the meaning of the M tantalizingly ambiguous. It could stand for magic, mystery, or, most importantly, membrane. M theory revealed that the fundamental objects in the universe were not just one-dimensional strings, but also higher-dimensional objects called branes. The term brane, short for membrane, could refer to an object of any dimensionality. A 0 brane is a point, a 1 brane is a string, a 2 brane is a surface, a 3 brane is a 3-dimensional volume, and so on, all the way up to a 9 brane. This new ingredient, the brane, led to a completely new and revolutionary cosmology, one that gave birth to yet another kind of multiverse. The idea, developed by physicists like Lisa Randall and Raman Sundram, was that our entire observable universe, with its 3 dimensions of space and 1 of time, might be a vast, expansive 3-brane embedded within a higher dimensional space, a reality with more dimensions known as the bulk. In this brane world scenario, all the particles and forces of the standard model, electrons, quarks, photons, the strong and weak nuclear forces, are manifestations of open strings, whose ends are permanently attached to our 3-brane. This is why we are stuck here, unable to perceive or move into the extra dimensions. We, and the matter we are made of are literally confined to our brain. But there is one crucial exception: gravity. According to the theory, the graviton is a closed loop of string. With no open ends to anchor it, it is not tied to our brain and is free to travel and leak out into the higher dimensional bulk. This provided a startling and elegant explanation for another deep mystery in physics: the weakness of gravity. Gravity is tremendously feeble compared to the other fundamental forces. The electromagnetic force of a tiny kitchen magnet, for example, can easily overcome the gravitational pull of the entire planet Earth. In the brain world model, gravity is not intrinsically weak. It just appears that way to us because its influence is diluted as it spreads out across all the extra dimensions, while the other forces remain concentrated on our brain. And this is where the multiverse enters the picture. If our universe is one brain floating in a higher dimensional bulk, what is to stop there from being other brains? M-theory allows for the existence of countless other brains, perhaps parallel to our own, each one a self-contained universe, potentially with its own unique particles and forces. These other worlds could be, in a sense, right next to us, separated by a microscopic distance in a higher dimension, perhaps less than a millimeter away. Yet they would remain completely invisible and inaccessible to us, forever beyond our reach, with the tantalizing exception of gravity, the one force that could, in theory, pass between the worlds, a ghostly messenger from another universe. These parallel and seemingly disconnected theories, one born from the explosive birth of our cosmos, and the other from the subatomic dance of vibrating strings, were converging on a shared, breathtaking conclusion. They both painted a picture of a reality far grander and more diverse than anything humanity had ever conceived. A vast landscape of other universes, perhaps infinite in number and variety. This theoretical blossoming of worlds, however, brought an old and deeply perplexing philosophical question crashing into the heart of modern physics. If there are countless other universes, many of which may have different fundamental laws and constants, why do we find ourselves in this one? Why is our universe so exquisitely, so improbably perfect for the existence of life? It is a question that arises because the more we learn about the cosmos, the more it seems as though it has been balanced on a knife's edge, a universe where a dozen different dials have been tuned to a razor-thin sliver of their possible values, creating the precise conditions necessary for stars to form, planets to coalesce, and for complex, conscious beings to eventually emerge and ponder their own existence. This is the great Goldilocks enigma. Our universe is not too hot, not too cold, but just right. Consider, for example, the strong nuclear force, the fundamental interaction that acts like a cosmic superglue, binding protons and neutrons together to form atomic nuclei. If this force were just 2% stronger than it is, protons would have fused together so readily in the inferno of the Big Bang that all the hydrogen in the universe would have been consumed, converted into helium. Without hydrogen, there would be no water, the essential solvent for life as we know it. There would also be no long-lived, stable stars like our sun, which burns by fusing hydrogen for billions of years, providing the steady, reliable energy needed for life to evolve. If, on the other hand, the strong force were just 2% weaker, protons and neutrons would not be able to bind together at all. Only the simplest element, hydrogen, would exist. The universe would be a sterile, featureless sea of hydrogen gas, with no carbon, no oxygen, no iron, and thus no chemistry, no planets, and no people. The value of this force is a parameter that could have been anything, yet it falls within the extraordinarily narrow window that allows for a complex and interesting universe. This uncanny fine-tuning is not an isolated case. It appears in numerous, fundamental constants of nature. Take the cosmological constant, the mysterious dark energy that is causing the expansion of the universe to accelerate. Its observed value is so small that it is difficult to even describe. A number so close to zero, it is like a 1 preceded by a decimal point and 120 zeros. Yet, according to our best theories, its natural value should be enormous, about 120 orders of magnitude larger than what we measure. If the cosmological constant were even slightly larger than its observed value, its repulsive force would have been so powerful that it would have torn the universe apart in its infancy, preventing matter from ever clumping together to form galaxies, stars, or any structures at all. If its value were large and negative, the universe would have collapsed back in on itself in a fraction of a second. The fact that we inhabit a universe with such a tiny but non-zero cosmological constant is perhaps the most extreme and baffling example of fine-tuning in all of physics. It is a value that has been tuned with an accuracy equivalent to guessing a single, specific atom from all the atoms in 1,000 observable universes. The list goes on, a cascade of cosmic coincidences. The neutron is just a tiny fraction of a percent heavier than the proton. If it were the other way around, with the proton being even slightly heavier, it would be unstable and would decay into a neutron, an anti-electron, and a neutrino. This would mean that hydrogen atoms, the basic fuel of stars and the most common element in the universe, could not exist, and the cosmos would be devoid of stable matter. The force of gravity itself is about 40 orders of magnitude weaker than the electromagnetic force, a power of 10 difference so vast it is like comparing the size of a single atom to the size of the entire Milky Way galaxy. If gravity were even slightly stronger, stars would burn through their fuel in a few million years, not the billions needed for complex life to evolve on their orbiting planets. If it were weaker, matter might never have coalesced into stars and galaxies in the first place. These constants appear to be independent of one another, a series of dials on a great cosmic control panel, and it seems that each one has been set with breathtaking precision to the one specific value that allows for a universe capable of hosting observers. Faced with this overwhelming evidence of fine-tuning, scientists and philosophers have been forced to consider three possible explanations. The first is that it is all a meaningless coincidence, a simple brute fact of our existence. We just happened to win an utterly improbable cosmic lottery, and there is no deeper explanation to be found. This view, however, is deeply unsatisfying to the scientific mind, which is predicated on the idea that the universe should be explicable. The second possibility is that the universe was designed. This is the ancient teleological argument, the idea that a divine creator or a superintelligence deliberately fine-tuned the cosmos with the specific intention of creating life. While this is a logically coherent explanation, it is one that lies outside the realm of science, as it posits a cause that is, by definition, supernatural and untestable. The third explanation is the one that brings us back to the multiverse. In the 1970s, the physicist Brandon Carter first articulated what he called the anthropic principle, which, in its most basic form, states that the universe must, of necessity, be compatible with the existence of conscious observers, like us, because we are here observing it. Carter proposed two versions of this principle. The strong anthropic principle suggests that the universe was somehow compelled to eventually have conscious life emerge within it, a highly controversial and teleological view. But it was his weak anthropic principle that provided a powerful new scientific tool. The weak version is not a statement about purpose, but about a selection effect. It simply notes that if the universe's properties were not compatible with our existence, we would not be around to notice. It is like a fish waking up and realizing that its environment is entirely filled with liquid water. This is not a surprising discovery, because if it were otherwise, the fish would not be there to make the observation. For decades, this principle was an interesting philosophical footnote, but it lacked any real physical context. It explained why we observe a life-friendly universe, but not how such an improbable universe came to be in the first place. The rise of the multiverse theories provided that missing context. If eternal inflation, or M theory, is correct, then our universe is not unique. Instead, there is a vast cosmic landscape, an infinite collection of bubble universes or brain worlds, and in each one, the fundamental constants of nature, the settings on those cosmic dials, could be different. In this scenario, the weak anthropic principle becomes a powerful predictive tool. The vast majority of these universes would be sterile wastelands where the dials are set to the wrong values, universes that collapse in an instant that are filled with nothing but black holes, or that contain no stable atoms. But with an infinite or near infinite number of universes, it becomes a statistical certainty that a small fraction of them, by sheer random chance, will happen to have the right combination of constants for life to emerge. We, as conscious observers, find ourselves in one of these rare, life-friendly universes for the same reason we find ourselves on a life-friendly planet. We did not win a single, impossible lottery. We simply live in one of the universes where winning was a possibility. The multiverse, therefore, transforms the fine-tuning problem from a mystery about a single, miraculous creation into a simple matter of statistics and observer selection, neatly explaining why our cosmic home is so perfectly suited for us, without recourse to either supernatural design or unimaginable coincidence. But this elegant marriage of theoretical physics and philosophical reasoning, for all its explanatory power, carries with it an immense intellectual burden. An explanation that invokes an infinite number of unobservable entities to account for the properties of our own observable world walks a very fine line between science and metaphysics. Science, at its core, is not just about telling a consistent and compelling story. It is a discipline built upon the unforgiving bedrock of empirical evidence, and most importantly, on the principle of falsifiability. This idea, most forcefully articulated by the 20th century philosopher of science, Karl Popper, holds that for a theory to be considered truly scientific, there must be some conceivable observation or experiment that could prove it wrong. A theory that explains everything and can be bent to accommodate any possible discovery ultimately explains nothing. And it is on this crucial point that the multiverse, in the eyes of many scientists, stumbles. How can you possibly test for, let alone falsify, the existence of universes that are, by their very nature, causally disconnected from our own? It is a challenge that threatens to push the entire concept out of the realm of physics and into the domain of pure, untestable speculation. And yet, the history of science is filled with concepts, from atoms to black holes, that were once thought to be purely theoretical constructs, forever beyond the reach of observation, only to be later confirmed by the sheer ingenuity of experimentalists. The physicists who champion the multiverse are not content to leave it as a philosophical curiosity. They have been engaged in a determined and deeply creative effort to drag the idea, kicking and screaming, into the world of testable science. They have been searching for ways that these other universes, if they exist, might have left a subtle, lingering trace upon our own, a faint whisper of their existence that we might be able to detect with our most sensitive instruments. The most promising place to look for such a signature is in the oldest light in the universe, the cosmic microwave background radiation. This faint afterglow of the Big Bang is not just a uniform sheet of light. It is a snapshot of the cosmos when it was just 380,000 years old, and it is modeled with tiny temperature fluctuations, primordial ripples that were the seeds of all the galaxies and cosmic structures we see today. If our universe is not alone, but is instead one bubble in a vast, eternally inflating ocean, then it is conceivable that in its infancy, our bubble may have bumped into another. Such a collision would have been an event of unimaginable violence, a cosmic fender bender that would have sent shock waves of energy rippling through the young, hot plasma of our nascent universe. This disruption, this cosmic bruise, would have left a lasting imprint on the fabric of space-time, a subtle but permanent scar on the cosmic microwave background. According to the models developed by physicists like Matthew Johnson and Laura Mersini-Houghton, such a collision would manifest today as a specific, large-scale, circular pattern on the sky. It might appear as a disc-shaped region that is slightly hotter or colder than the surrounding background, or it might have a distinctive pattern in the polarization of the light. Finding such a disk, a statistically significant circular anomaly that could not be easily explained by the standard model of cosmology, would be a revolutionary discovery. The first piece of tangible evidence that our universe is just one of many. Armed with these theoretical predictions, cosmologists have embarked on a meticulous search, poring over the incredibly detailed maps of the cosmic dawn created by space telescopes like NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, and the European Space Agency's even more powerful Planck satellite. They have run sophisticated computer algorithms across these celestial maps, scanning for any hint of these telltale bruises. While some intriguing anomalies and alignments have been found over the years, none have so far risen to the level of a definitive smoking gun detection. The signals are faint, the data is noisy, and the patterns remain tantalizingly ambiguous. There is, however, one feature on these maps that has stubbornly refused to be ignored. An anomaly so large and so statistically improbable that it has been given its own name: the cold spot. First discovered in 2004 in the data from the WMAP satellite, and later confirmed with much higher resolution by Planck, the cold spot is a vast patch of the sky, stretching over 1 billion light-years across, that is anomalously and inexplicably cold. It is not just a minor dip in temperature. It is a deep and profound chill, a region whose temperature deviates from the average far more than the standard theory of cosmic inflation, which is based on random quantum fluctuations, would predict. The probability of such a large and cold spot appearing by chance is less than 1%, making it one of the most significant pieces of evidence for physics beyond the standard cosmological model. And one of the most exciting, if speculative, explanations for the cold spot is that it is the very cosmic bruise that theorists have been searching for, the remnant of a collision between our bubble universe and another that drained energy from that region of space, leaving it colder than its surroundings. This tantalizing possibility, however, has a more mundane, though still fascinating, rival explanation. The apparent coldness of the spot might not be an intrinsic feature of the primordial radiation itself, but an illusion created by something the light has traveled through on its 13.8 billion-year journey to our telescopes. Astronomers have theorized that the cold spot could be caused by a supervoid, an absolutely immense region of intervening space that is almost completely devoid of galaxies and matter. According to general relativity, light from the cosmic microwave background gains a small amount of energy as it enters the gravitational well of a large structure like a galaxy cluster, and then loses that energy as it climbs back out. But if the universe's expansion is accelerating due to dark energy, the structure will have expanded while the light is passing through it, and the light will not regain all the energy it lost, resulting in a slight net cooling. A supervoid would have the opposite effect, but a vast and empty one could create a cold spot. To test this, astronomers have pointed their telescopes towards the direction of the cold spot, meticulously mapping the three-dimensional distribution of galaxies. And they have, indeed, found a large void, one of the biggest ever discovered, stretching over 1.8 billion light-years. The great debate now raging in the astronomical community is whether this void is large enough and empty enough to fully account for the observed coldness. Some studies say yes, that the void explains everything. Others insist that it can only account for a fraction of the temperature dip, leaving the multiverse collision hypothesis very much on the table. The jury is still out, and the cold spot remains one of the most profound mysteries in modern cosmology. And this is not the only avenue of investigation. Proponents of the brain world multiverse, born from M theory, are pursuing different clues. They suggest that if another brain universe is just a fraction of a millimeter away from ours in a higher dimension, we might be able to detect its gravitational influence. Experiments at the Large Hadron Collider near Geneva, Switzerland, have searched for signs of energy from particle collisions vanishing from our detectors, as if it were leaking away into these extra dimensions. So far, no such evidence has been found. The search continues on the grandest and smallest of scales, a difficult and often frustrating quest, but one driven by the knowledge that a confirmed discovery would not just be another scientific advance, but a fundamental and permanent recalibration of humanity's place in the cosmos. The relentless and so far fruitless search for a definitive cosmic bruise or a whisper from another dimension has done little to dampen the enthusiasm of the multiverse's proponents. For them, the theories of eternal inflation and the string theory landscape are not just speculative flights of fancy, but are the most natural and logical extensions of our current understanding of fundamental physics. They argue that these theories solve profound problems in cosmology and particle physics, and that the existence of a multiverse is a direct and unavoidable consequence of taking their mathematics seriously. The lack of a direct evidence, they contend, is not a failure of the theory, but a reflection of the immense technological and conceptual challenges involved in probing such an extraordinary reality. They believe that we are in a position similar to that of the ancient Greek atomists, who correctly deduced the existence of atoms 2,000 years before humanity developed the tools to finally see them. The multiverse, they insist, is a prediction of our best science, and to reject it simply because it is difficult to test or because it offends our philosophical sensibilities is to abandon the very spirit of scientific inquiry. This bold and confident stance, however, has ignited a fierce and deeply philosophical debate that has split the physics community, a schism that goes to the very heart of what science is and what it should aspire to be. On the other side of this great divide are the skeptics, a formidable and vocal group of physicists who view the rising popularity of the multiverse with a mixture of frustration and alarm. They see it not as the next great leap in our understanding of the cosmos, but as a dangerous and seductive departure from the core principles of the scientific method, a slow slide into a kind of post-empirical science, where mathematical elegance and explanatory power are valued more highly than experimental verification. For these critics, the multiverse is not a scientific theory at all, but a grand and elaborate metaphysical framework, a theory of anything that, by its very nature, can explain any observation and is therefore scientifically vacuous. It is a criticism that strikes at the very foundations of the multiverse hypothesis, its utter lack of falsifiability. The leading charge against the multiverse is often championed by physicists like George Ellis and Paul Steinhardt, who argue that any theory that makes untestable predictions is by definition not science. Ellis, a distinguished cosmologist and a one-time collaborator of Stephen Hawking, has been a particularly trenchant critic, arguing that the multiverse is a beautiful story, but one that will forever remain in the realm of faith rather than fact. He points out that all the proposed observational tests, such as the search for cosmic bruises, are highly speculative, and even if a signal were found, it would be almost impossible to definitively prove that it was caused by another universe and not by some new, unknown physics operating within our own. The core problem is that the multiverse theories, particularly eternal inflation and the string landscape, do not just predict a single, specific multiverse. They predict a near infinite variety of multiverses with different properties, creating a theoretical framework that is so flexible it can be made to fit virtually any data. If we discover a cosmic bruise, the theory can accommodate it. If we do not, the theory can explain that too, perhaps by stating that collisions are simply very rare. A theory that can predict anything, the critics argue, predicts nothing. Paul Steinhardt, one of the original architects of cosmic inflation theory, has become one of its most prominent critics, largely because of the multiverse it seems to inevitably produce. He calls it the problem of the measure. In an eternally inflating multiverse, where every possible outcome occurs an infinite number of times, it becomes impossible to calculate the probability of any particular event. Without the ability to assign probabilities, one cannot make meaningful predictions. How can you say that our universe's finely tuned constants are unlikely when in an infinite multiverse, every possibility, likely or unlikely, is realized an infinite number of times? To solve this, theorists have to impose an arbitrary mathematical measure to regulate these infinities, a way of taming them so that probabilities can be calculated. But there is no consensus on which measure to use, and different measures give wildly different answers. For Steinhardt, this is a fatal flaw, a sign that the theory has lost its predictive power and has become a kind of theoretical blank check. He argues that this makes cosmic inflation itself untestable, as any future observation, no matter what it is, can be explained as just one of the infinite possibilities realized in some corner of the multiverse. This, he fears, marks the end of a productive feedback loop between theory and experiment that has driven physics forward for 400 years. This critique extends to the use of the anthropic principle, which the skeptics view not as a powerful explanatory tool, but as an intellectual surrender, a lazy way of explaining away the fine-tuning problem. Invoking an infinite number of other universes to explain the properties of our own, they argue, is a violation of Occam's razor, the principle that one should not multiply entities beyond necessity. It is the ultimate ad hoc explanation. The physicist David Gross, a Nobel laureate for his work on the strong nuclear force, has compared it to the ancient practice of explaining the orbits of the planets by invoking the will of angels. By stating that our universe has the properties it does because we are here, the anthropic argument seems to shut down further inquiry, discouraging the search for a deeper, more fundamental explanation for the values of the physical constants. The critics argue that we should not give up on the hope of one day finding a unique and compelling theory, perhaps a final version of string theory or some other framework, that demonstrates that the constants of nature must have the values they do for reasons of mathematical consistency, with no other options possible. To them, the multiverse is an admission of defeat, a declaration that the fundamental properties of our universe are nothing more than a random accident of our cosmic address. At its core, this is a debate about the soul of physics. The proponents of the multiverse argue that we must follow the mathematics where it leads, even if it takes us to a reality that is far stranger and less accessible than we had hoped. They believe that the universe has no obligation to be easily testable by us, and that our definition of science may need to expand to accommodate theories that are so fundamental that their direct verification is beyond our technological grasp. They contend that a theory's internal consistency, its mathematical beauty, and its ability to resolve deep conceptual paradoxes can also serve as a form of evidence. The critics on the other hand, hold fast to the traditional demarcation between science and non-science, insisting that a theory's connection to empirical reality is non-negotiable. They fear that if the physics community embraces untestable theories like the multiverse, it will lose its intellectual credibility and become indistinguishable from philosophy or even theology. It is a profound and unresolved conflict, a sign that physics has pushed to the very edge of what can be known, a place where the familiar signposts of observation and experiment begin to fade, and the path forward is shrouded in a deep and unsettling fog. The great debate over the multiverse is not just about whether other worlds exist. It is about the limits of science itself, a struggle to define the rules of the game in a cosmic arena that has suddenly become vastly larger and more mysterious than we ever imagined. And so, our journey through this unfolding map of reality comes to a close. A journey that has carried us across more than 2,000 years of human thought in a quest to understand our place in the cosmos. We began in the sunlit marketplaces of ancient Greece, where the atomists, with nothing more than the power of pure reason, first planted the seed of an idea that an infinite supply of atoms in an infinite void must logically create an infinite number of worlds. We saw that seed lay dormant for well over a millennium, buried beneath the weight of an earth-centered single-universe dogma, until it was reignited with the fire of a heretic's conviction by Giordano Bruno, who envisioned an infinite creation for his infinite God and paid the ultimate price for his cosmic vision in a Roman square in the year 1600. From the philosophical flames of the Renaissance, our story jumped to the strange, probabilistic world of the 20th century. We met the brilliant and iconoclastic Hugh Everett III, who, bothered by the strange paradoxes at the heart of quantum mechanics, made a breathtaking leap of imagination. By simply proposing that the wave function of reality never collapses, he unleashed a near infinite, ever-branching tree of parallel universes, each one a tangible reality where every quantum possibility is played out. At the same time, we saw how cosmologists, wrestling with the puzzles of our own universe's origin, independently arrived at a similar conclusion. The theory of cosmic inflation, our best explanation for the Big Bang, led to the startling vision of André Linde's Eternal Sea, where new bubble universes, each with potentially different physical laws, are constantly budding into existence. And from the opposite end of the scale, in the search for a theory of everything, the elegant mathematics of M-theory painted a picture of our universe as a single brain floating in a higher dimensional space potentially filled with others. We have seen how these vast theoretical landscapes provided a powerful, if controversial, answer to the profound mystery of our own existence, the Goldilocks enigma of our universe's uncanny fine-tuning. The anthropic principle, when combined with a multiverse, suggests that we find ourselves in a life-friendly universe for the same reason we find ourselves on a life-friendly planet. It is a matter of selection from a vast number of less hospitable alternatives. This transformed the multiverse from a mere abstract consequence of theory into a tangible hypothesis with potential, albeit faint, observational signatures. We followed the ongoing search for these signs, scanning the ancient light of the cosmic microwave background for the faint bruises of a cosmic collision. A search that has so far yielded tantalizing anomalies, like the cold spot, but no definitive proof. Ultimately, we have seen that this grand idea now stands at a crossroads, celebrated by some as the ultimate expression of scientific naturalism, and condemned by others as a dangerous departure from the empirical rigor that has defined science for 400 years. It is a debate that forces us to ask what it means to know something, and whether the universe is obligated to conform to our methods of inquiry. Whether the multiverse is a reality we will one day confirm, or a grand illusion born from our incomplete understanding, the quest itself has irrevocably changed our perspective. It has forced us to confront the possibility that our entire cosmos, with its trillions of galaxies and billions of years of history, might be just one page in a library of infinities. The story of the multiverse is the story of humanity, looking up at the night sky and, for the first time, daring to wonder if the darkness between the stars is not an emptiness, but the space between the pages of a book far grander than we ever knew how to read.